All right, this is for my online students to try to help them with this BCHS Physics Lab number 7. So you can open your lab into Pivot, um, which you'll have a link in Google Classroom to open it to. It's called Lab number 7. Watch the video of the cart that's moving along a frictionless track as a hanging mass applies to the force on the cart once the string is cut. So someone's going to cut the string and the cart's going to start to accelerate to the left. We will assume, this is a big assumption, we will assume that the force of tension equals the force of gravity acting on the hanging mass. So I'm going to take you over to that lab here in a minute, but here is my cart. It has a string that's going to go through a little pulley and come down with a hanging mass. Let me draw that a little bit better. Okay, and that hanging mass is going to descend and eventually hit, looks like a piece of clay or something. Okay, nevertheless, there's a diagram of what's occurring. So let's go and look and see what this looks like. And so hopefully my online students can see that. Here is, I have the ability to change my hanging masses and I have the ability to change the system mass. The system mass is the mass of the car. Okay, we're going to need that. So I'm going to put it to 20 and then I'm going to load that video and I have a picture now and we'll go ahead and take a look at what it looks like. Someone just cut the string and the cart is now accelerating downward. You can see the hanging mass is descending and eventually the hanging mass is going to hit the clay and the car is still going to the left, but the tension is no longer there. So the force is gone. Okay, so there are two parts of this problem. At the moment she cuts the string, I now am putting a force on the car, it's accelerating, and then you'll notice right as I hit the clay, my tension force, look at the bottom near the clay, goes to 0 and the string goes slack, but there's still a motion, the car is still moving. So now let's go back to here. What we need to do first is show the free body diagram of the forces acting on the cart as the hanging mass is descending. So before it hits the clay. So here is my dot that represents my cart. And I have force normal and I have force of gravity. And those should be equal. And I probably didn't draw those vectors quite the same. And then I have this force that's pulling the cart and we call that force of tension. Okay. Now we assume that that force of tension is equal to the force of gravity that's acting on that hanging mass. So I can actually calculate that force of tension based on that assumption. Whether or not that's a good assumption or not, we can discuss that. Include on the diagram the displacement vector. So I'll put that in blue. Here is the displacement vector that the cart is moving to the left, so its displacement vector is to the left. So this is the free body diagram of the cart before it hits. What is the equation for work? Work is equal to the force that's doing the work times the distance times cosine theta. And in this case, what is the force doing the work? There's only one force doing the work, and that is force of tension. And the distance we can measure. And cosine theta is 0 degrees because there is no angle between the direction of force of tension and the displacement vector. There is 0 angle. Okay, so this we can measure. This we're going to calculate. All right, so what is the only force doing work? Well, there's 3 forces doing that are acting on the cart, but the only force doing work, so how do I answer the question, is force of tension, because force of gravity, force normal do no work. Why? Because theta equals 90 degrees and cosine of 90 is 0. Okay, now I'm going to show you how to collect data for one, and then my online students, if you can give me 2 more, that'd be great. So we're going to, actually, I probably should have had one out here to call the system mass. And so I'm going to use the one that we just loaded, which was 400 grams. So we're going to call this run 1. The hanging mass was 20 grams. I'm going to convert that into kilograms. We have to calculate force normal, or force, not force normal. We have to calculate the force that's acting on that, which is the force of tension. And we said that the force of tension was going to be equal to the force of gravity that's acting on that hanging mass. So it's going to be mass times gravity, and we knew the hanging mass to be 0.02 kilograms, and we know gravity to be 9.8 meters per second squared. And so in this case, that force will be 0.196 newtons, 0.196 newtons. Now we've got to go and find this distance that the actual hanging mass was creating that tension on that car. So I have to go to my lab, move this back, and I'm going to notice that, okay, she cut the string. I'm going to measure how far did the car travel. So maybe I have it on the edge of the cart. Did it travel before the tension went to 0? So I'm now looking at the hanging mass, and as soon as it hits, oh, there it is. And I estimated that distance. Now I can see where it is. Now the force is no longer there. So the force acted on that car, I estimated to be 41.5 centimeters. And I converted that to meters. So that is 0.41, I said 5 meters. So this distance, D, is the distance that the car was exposed to the tension force. Okay, so you got to measure that. Now I'm going to calculate work. How do I do that? Work equals FD cosine theta. So I can figure out work, FD cosine theta. Well, we found the force to be 0.196 newtons. We had the distance to be 0.415 meters. And we said cosine, and that angle is 0 degrees. And so we found that work to be, I estimated, 0.081 joules. All right, now construct a free body diagram of the forces acting on the cart after the hanging mass has hit the table. So if I look at that, he's traveling to the left, and the tension force is gone. So the string is no longer pulling on it. Okay, oops. So what does that free body diagram look like? And this is one that people struggle with to see conceptually. That's force normal. This is force of gravity. He's still traveling to the right, and there's no other forces. And everyone wants to know, well, where's the force applied? Well, it's gone because the tension force is no longer there. So we know that in this situation, and oh, by the way, we assume the track is frictionless. Acceleration is equal to 0, V is constant. And because of this fact, I can now measure the speed. If I measure how far it goes, measure D, measure the time, I can calculate the speed that it is currently at after that force had done some work. So let's go do that. So I need my stopwatch. I need to start right. I'm going to move this out of the way and watch the hanging mass. The hanging mass is going to hit. Oh, there it is. It hit. Force is gone. I'm going to say that's 0. And I'm going to say, okay, well, let's see how far it goes over some period of time. So now I'm at 0 clock. I'm at 0 centimeters. And let's just go approximately 40 centimeters. And it takes 0.633 seconds to go that far. Now I can calculate some speed. So again, this is still run 1. This is system mass was 400 grams. That's what I had loaded. I'm going to convert that to kilograms because we're going to need it. And I just measured that distance to be 40 centimeters, which I need to make in meters. I measured the time that it took to do that at 6.663 seconds. And I calculated the speed then to be 0.6314. Okay, and let me show you an example calculation. So the first thing was speed. So I had speed equals 0.4 meters over 0.633 seconds. That's that final velocity of that car. Oh, no, what am I doing? I'm copying the wrong thing. I found that to be 0.314 meters per second. Sorry, 634. Okay, one last thing. If you needed to see the distance, which I found to be 40 centimeters, 100 centimeters equals 1 meter, and that's how I got 0.4 meters. I need to know the final kinetic energy of the car. So let's take a look at the car. So here he is. He had a velocity initial of 0. So his kinetic energy initial was 0. And then this force was being applied. And then what is its final kinetic energy? Well, I need to know its final velocity. Well, we just measured its velocity because it's constant. We just measured it. And that was this 0.6314 meters per second. So I got to calculate that kinetic energy final. So kinetic energy final is equal to 1/2 the mass times V final squared. What was the mass? Well, the mass is the system mass, the mass of the car. That's what we're interested in. And it needs to be in kilograms. And then that final velocity needs to be in meters per second. And we already calculated that to be 0.6314 meters per second. I'm going to square it, and I now have a final kinetic energy of 0.0797 joules. Whoops. And I don't really have to put joules in there since it's already on top, 0.0797. Okay, what's the kinetic energy change minus initial? Well, initial 0 because the car started from rest, and so the final kinetic energy is essentially the change in kinetic energy. Okay, that was kind of just helping you see that. And then, okay, continuing on. Since the only work that's being done is the force of tension, that work that we calculated on the first page is the net work, the force being done by the net. And we know that that is supposed to equal, come on, the change in kinetic energy. Come on. There we go. So what we're trying to do is compare this network to the change in kinetic energy and see if they're the same. So we have run number 1, and I'm going to get this from page 1, first page. Okay, so we calculated the work by measuring the force, and that's 0.081 joules. Okay, 0.081 joules. And we calculated the change in kinetic energy, which was equal to 0.0797 joules. And then we figured out the percent error. So here's my equation for percent error. So let's do one. Percent error is equal to the change in kinetic energy, which is 0.0797, minus the work that we found from page 1, 0.081, divided by the change in kinetic energy. And we're not going to worry about it. If it's negative, we're going to take the absolute value. We're going to multiply it times 100%. And in this case, we found it to be 1.59%. Okay. All right. For online students, if you wanted to give me at least 2 on your own, 2, I'm going to say 3 and 4 because I'm going to give you 3 and 4, and I'm going to, I'll pick a couple for you. How about 3? We're going to make it at 60 grams with 600 grams for a system. And 4, I'm going to put 100 grams at 800 gram for a system. So you'll need to load the proper apparatus, okay? All right, now, I'll give you some data for another one in case you'd like to check your approach. So this is number 2. I'll give you, it is 400. This is 60 grams. That would be equal to 0.06 kilograms. I found the force of tension to be equal to newtons. I have the distance that traveled approximately 42 centimeters, and the work was 247 joules. And then this over here would be, again, 400 grams, which is 0.4 kilograms. And I measured in 40 centimeters. It took a time of 0.3667 seconds. And I calculated that speed to be approximately 1.091 meters per second. The final kinetic energy using the proper mass and final velocity was 0.238 joules, which is the same as the change in kinetic energy. This is run 2. I pulled the numbers from page 1, 0.247 joules. This was from page 2, which was 0.2383 joules, and I found that percent error to be approximately 3.78% error. Okay, so there's a couple of data points, and then you're going to do 2 on your own. Hope that helps.